Hello, this is Abhishek Gade, and today we will be talking about the zero gradient boundary condition in OpenFOAM. So let us start. So first of all, what is a gradient? Gradient means let us take two variables. One is phi and one is n. Phi can be anything. We can say it as velocity, we can say it as a temperature, and n can be the x distance, the y distance. So a change in this phi value, if I go, this is the line of that function where phi is dependent on n, this is the line. So how much the phi is changed divided by how much change in n for the same change in phi. How much change in n will give this much change in phi. So delta phi upon delta n is the gradient. Having understood gradient, let us move on to what is zero gradient. So zero gradient sets the value of variable at the patch equal to the internal value in the nearest cell. So a cell has a center. So a face and a nearest cell. The face center value would be equal to the nearest cell center value. This is the meaning. And what can we say? It is zero gradient, means the variable is fully developed on that patch. The direction here we are considering is perpendicular to the patch or the boundary which we are talking. And this is a type of Newman boundary conditions. Newman boundary conditions means where the gradient is specified, and here it is specified. Here it is del phi by del n is equal to 0. Okay. So how to use this in OpenFOAM? We specify it by writing the patch name. At the patch name, we will write what boundary we want this zero gradient, and this we will be writing in the variable file which we want to apply, in which we want to apply the zero gradient. So in curly brackets, we will write type zero gradient, and this is how it is specified in OpenFOAM. Simple. Let us understand what is its meaning, how actually OpenFOAM is doing inside this, how it is considering the zero gradient inside. So let us first discretize the Laplacian term in the Navier-Stokes equation at the boundary. So this is the face which is shown in yellow color. The cell center value to the nearest neighbor cell is phi p. So this is the cell center, and the face has the center phi b. So phi p and phi b, these are two values, and both of them are separated by a distance of magnitude d. The surface area vector is pointing out normally SF. Now let us take see the discretization. So this is the term integral over the volume of gamma dot grade gamma. So gamma dot grade dot gamma grade phi. So grade dot gamma grade phi means gamma is diffusion coefficient. Gamma is diffusion coefficient, and this is the Laplacian term. Now this is actually a volumetric integral. First we will have to convert it into surface integral. So surface integral, we can convert it using the Gauss divergence theorem, and yes, we converted it. So now we have n ds, so and it is integral over s. Now this is over a surface. We changed from volume to the surface. But can we write it as sigma? Yes, because it is all the integration means the summation of all the small faces. So we will sum it over the entire face. So all that small faces taking into consideration, we can write it in this form: gamma f sf dot grade phi f. So this grade phi gamma f, this is for right now for boundary. This is the general expression, but right now we are considering it at boundary, because we need to give zero gradient boundary condition. And so this f will become b at last, and I can write it like this: grade phi f, when it is opened, it will be phi b, means this value, minus phi p, the nearest phi value from the center I am taking now, divided by the distance between them, and this sf will become magnitude sb. Okay, so this is how the discretization is done. Now let us apply the zero gradient boundary condition. We know this term, the gradient term, which we opened right now. This is equal to 0. What does this mean? So in the matrix, overall matrix, the coefficient matrix, there would be no contribution because everything is becoming 0. There would be no contribution in this coefficient matrix itself, as well as in the source, there would be no contribution. And suppose we write it like this: grade phi b would, if we write it like this, like gradient internal coefficient, that is CGI phi p plus CGB. CGB is gradient boundary coefficient. We just now saw everything is becoming 0. That means from nowhere there is contribution, means CGI would also be equal to 0. CGB will also be equal to 0. And this is how it is specified here. See, gradient internal coefficients and gradient boundary coefficients in OpenFOAM, it is set to 0. This we are talking about the zero gradient FV page field dot C. So in that C file, this is how it is implemented. Yes. Now we'll move on. Having understood how to discretize Laplacian term and how the matrix is affected, let us now see how the convective term discretization takes place. So convective term discretization, again we'll consider this phase which is shown in yellow color. The value of that variable is phi b here, and at the center phi p. So discretization of convective term. Okay. So integral over the volume grad dot u phi. Again, converting it into surface integral, we have n ds, the dot with u phi. And now again, integration can be written as summation over the entire surface. So I am writing it like this: sf dot uf phi f. Now if I consider, okay, this is the summation over the entire face, all the small values, but we can see this is sf, this is uf, this is area, and this is velocity into that area, that would actually give the flux. And so I can write it as ff. Okay, so that means ff phi f, the summation over the entire face. That is how the convective term discretization takes place. Now ff phi f can be written as fb phi b, because we are talking right now at the boundary. Okay, so uh, okay, so we just now saw phi b minus phi p upon the magnitude of this distance between them should be equal to 0. That means this and these two values are same. Okay, so phi b is equal to phi p. From this expression here we get this. That means both the variables are same. Okay, so but we want to know, in the previous slide we saw, we want to know what is fb phi b. Now what is fb phi b? Because phi b is equal to phi p, we can write it as fb phi b is equal to fb phi p. So one thing to note here, phi p, which is still unknown, that is taken as the boundary. Directly we consider it for boundary after discretization, but phi p is still unknown. So where, in which matrix it will be? So in this matrix there is no source term. Okay, something which is unknown we have, that is phi p, means fb will come in this coefficient matrix here, and phi p would be somewhere here. So yes, this time the diagonal elements would be having, there would be some contribution in the diagonal elements from this part, and but for the source term still there is no contribution from zero gradient boundary condition discretization. Again we can write it like this: fb phi b can be written as fb cvi phi p plus cvb, where cvi is the value internal coefficients and cvb is the value boundary coefficients. See, compare these two values, the upper value and this expression. What can we see? Clearly we see that if we keep something as 1 and something as 0, we will get this expression. What is that something? This CVI if kept as 1 and this CVB if it is kept as 0, this equation will become FB phi P, means same as this. Yes, this is how it is implemented in OpenFOAM. See, value internal coefficients and 1 is given, and this value boundary coefficients and 0 is given. So this is how the zero gradient boundary condition, we use this many times, like, but we don't know how actually what is happening inside. This is how it is implemented in CFD. So this is all about the talk right now. And if you like my channel, like this video, you can support me at PayPal. And yeah, thank you.